next unit, we're going to be expanding our basic knowledge of integration, and eventually by the end of Chapter 8, we're going to be looking at integration with a bound that might be infinity or a negative infinity. But we're going to start things out here in this first section of Chapter 8 with some basic integration formulas. I have a list of 22 of basic formulas here in the notes. But in the Start Here module in Blaze View, there is a much longer list of integration formulas, and so these are repeated in that list, but I just want you to know this is not a comprehensive list by any means, but for this section, this list should be sufficient for you. Now, I'm going to do several examples here, and some of the examples are going to use the same formula because some things are going to come up more often than others. For some of the examples, we're going to have to do U substitution. Some of them we're going to do long division with polynomials. Some of them we're going to use some of the trig identities. So I'm going to try to give you a nice comprehensive sample here. We're going to look at the first two, and I'll tell you off the bat that the first two examples are both going to ultimately use the third formula here. We're going to be looking at some natural logs when we integrate, but you might not see that at first glance. The first one asks us to integrate from 0 to 1, 16x over 8x squared plus 2 dx. So in this one, I'm going to do a U substitution. I'm going to let U equal the denominator, 8x squared plus 2. And if U equals 8x squared plus 2, then the derivative of that, du, is going to be 8 times 2, or 16x dx. Well, convenient for us, u is the denominator, and the numerator, the 16x, the dx, there's our du. So I'm going to be integrating 1 over u du, and I'm going to adjust my limits here, my bounds of integration, to match this new u value. If x is 0, 0 squared is still 0, 8 times 0, still 0. So we end up with 0 plus 2, or 2 for that lower bound. And if x is 1, 1 squared is 1, 8 times 1 is 8, 8 plus 2 is 10. So now this is very straightforward. To integrate 1 over u du, you're just looking at the natural log of the absolute value of u. And that's that formula 3 up above. I'm going to look at that from 2 to 10. Since 2 and 10 are both positive numbers, we'll be able to drop the absolute value bars. So I've got the natural log of 10 minus the natural log of 2. One of the properties of logarithms is that I can rewrite this as one logarithm, dividing 10 divided by 2. So I've got the natural log of 10 over 2. So that's the natural log of 5. So that one is a relatively straightforward. We just did a u substitution and went straight to that formula. So the second example I'm going to do here, believe it or not, we're going to end up at that same place, 1 over u du. It just doesn't look like it maybe right now. The second one here, it's the inside there. We're going to take the integral of the natural log of y over y plus 4y times the natural log of y squared dy. So right now it just kind of looks like a big mess. What I'm going to do first is I'm going to factor out the y from the denominator. So that gives me y, and then I'll do a bracket here, times 1 plus 4 times the natural log of y squared. So a lot of times when you're working with these and you're trying to integrate, sometimes you have to just play around a little bit to decide on the best path, because sometimes there are multiple ways that you can work these problems. So a lot of times when I approach one of these, if I can factor, I'll try to factor something out. Also, a lot of times the U substitution is our best friend. And I often will look for the most complicated part of the integral to say, okay, maybe that's what U is going to equal. So in this case, I'm going to set U equal to 1 plus 4 times the natural log of y squared. So kind of what looks the messiest, let's set U equal to that. Now, to differentiate this, to find that du, obviously the 1 goes away, but we're going to use the chain rule over here. So I've got 4 times 2, or 8 times the natural log of y. Then I have to, again, using that chain rule, I'm going to have to differentiate the natural log of y, and that's going to be 1 over y dy. Well, if I look back at what I have, here's the u down here, what I put in the brackets. Here's the natural log of y, that's part of du. The 1 over y would be the y that's here in the denominator that was factored out. Obviously, here's the dy. So the only thing that I'm missing is the 8. I can go ahead and put in 8 here as long as I put a 1/8 in front. So ultimately, what do I have? I've got 1/8. Again, in the brackets is u, the 8 times the natural log of y over y dy, that's my du. So all I have is 1 over u du. We can integrate that. That's just the natural log of u. Plus c. Since u equals 1 plus 4 times the natural log of y squared, I'm going to go back and resubstitute that in. But I'm going to be able to drop the absolute value bars here because the natural log of y squared is always going to be positive. So this u value is always going to be a positive value. So I've got 1/8 times the natural log of 1 plus 4 times the natural log of y squared plus c.